Okay, so today we can continue our discussion on diffusion. Um, and this will just take us, I think it's only take like maybe 20 to 30 minutes to finish all the new topics that I want to talk about diffusion. And we're going to use the rest of the time to go through the homework problems in detail. Given the feedback that I got from the last time, I think, we can probably spend more time going through the problems in the homework to demonstrate that how we can apply what we know about the fundamental concepts and connect these to some real problems and gain some problem solving skills. So I think we're going to do that for the diffusion. And then we're gonna, say something about the exam, which I think based on some feedback I have from you guys, have a better idea of what the best format we could have. So that's the plan for this class. Okay, so about the diffusion, in the last class, I think we have finished our discussion of the interstitial diffusion. So we introduced that by working out a very simple material model, right? And we derive the Fick's laws. And in the Fick's first law, we show that diffusivity, which is one of the most important dynamic parameters related to diffusion, is determined by the physics in the sense that it's related to the hopping rate, related to the crystal structure of the material, and it relates to the free energy barrier for the hopping, etc. Right? But then we move on to work out the mathematics of the diffusion equation, and we introduce two different useful techniques for solving these, including the separation variables and Green's functions method. And we demonstrate that we can use the solutions and learn a lot of interesting physics about the corresponding processes, right? We worked out the harmonization of density fluctuation in detail, and we also demonstrate the carbonization processes as well. And then we move on, right? Say all of the mathematics that we described at this stage are for interstitial diffusions, right? But we know that in a solid material, there are definitely more than one type of point defects, right? You have interstitial defects, but you also have, these substitutional defects and vacancies and all of these type of things. And we know for a fact that all these defects also, they move around in random fashion in the material system, and they play important role in determining different physical properties of the material system. So it's very important for us to understand their diffusion as well. So the first thing we want to do here is that whether we can generalize all of the mathematical descriptions we have for the interstitial diffusion to different type of point defects diffusion. Okay, and the answer is yes, right? But we have to justify this. So we start with this, substitutional, in combination with vacancy diffusion case, right? So basically, in this case, we have a crystal structure, and we focus on one particular atom in this crystal structure. Now, this atom can be from the original material, okay, or it can be a substitutional atom, okay, if you consider the rest of these are copper, this can be aluminum, or this can be a copper as well. So as long as this atom takes the substitutional side, it doesn't really matter what this is. It's just we pick one atom and color it to be red so that we're tracking this atom, right? And then I think one important thing is that, so in order for these atoms to move around, right? So in order for the substitutional diffusion to occur, a necessary condition is that you have to have some concentration of vacancy in the system, right? Because the mechanism for the diffusion for the substitutional atom is that this guy gonna, at some time gonna receive a sufficiently high activation energy from the thermal fluctuations, right? And making a hop from this original location to this vacancy site, right? After that, you can get this configuration. So I think in the last lecture, we consider the ideal case that if the crystal structure or the material is a perfect crystal, okay? It's a perfect single crystalline material, okay? It might be very small in size, but in principle, we can make it a perfect crystal. And we know that, there will be no diffusion in that system. There's no substitutional diffusion, right? Because there's no vacancy for any atom to move into, so there will be no transport of atom in this particular scenario, right? So a necessary condition that for substitutional diffusion is that you have to have a certain concentration of vacancy. Okay, if your concentration of vacancy is very small, okay, you can expect that these diffusion for the substitutional diffusion would be fairly slow, right? Because you have to wait until there's a vacancy site nearby for the hop into. So this is quite intuitive and very interesting distinction from the interstitial diffusion and the substitutional diffusion, right? In the interstitial diffusion case, we know that the particles are taking these sites, right? And in most of the cases, we're only looking at a low concentration of interstitials. So, they're almost free to move around and free to hop into any of the neighboring sites. But here, for substitutional atom, it's quite different. It has to wait until there's a vacancy nearby and then hop into this vacancy site, right? So that's the, intuitively the difference between diffusion of different type of atoms. However, if we're looking at mathematics, right, do you think the mathematics we derived for interstitial diffusion also holds here? Or do you think the Fick's laws are still good for describing the substitutional diffusion / vacancy diffusion? The answer is yes, right? Because mathematical wise, there's no quite distinction describing this random wave of motion, right? If you think it's difficult to look at the substitutional particles, just think about a vacancy, right? Because the substitutional diffusion is equivalently can be described by the vacancy diffusion, because these two are basically the same processes, but looking at different atoms. If you're thinking there's a vacancy right here, right? And this vacancy can hop into any of the nearby locations where there's a real atom, right? And usually we consider the vacancy concentration is low, so the majority of the neighbors are just the real atoms the vacancy can hop into, right? So, and if you have certain vacancy concentrations, you basically imagine that if I have an imaginary plane, there will be certain number of vacancy cross from left to the right, and there will be some vacancy cross from right to the left, right? If you imagine this process is exactly the same as the interstitial diffusion that we work with, derive the Fick's laws, right? So it's quite easy to, see that the basic mathematics, like the Fick's laws that we described for these systems, still holds true, right? In this particular case, right? Assuming that my vacancy is not going to be destroyed or it's not going to be created, right? I have the, same number of vacancy in the material in the beginning and end of this diffusion processes. So I have both the Fick's first law, tell me the flux and how the flux is related to the concentration, and also have the continuity law. Okay, and combining them, I still have the overall diffusion equation. So that is quite clear. But the interesting thing is, because the mechanism, right, of the diffusion is different, right? In the case of interstitial diffusion, we have the atoms that are sitting in the interstitial sites and they hop into the nearby available sites. But in here, we have to wait for vacancy in order for the substitutional particle to do a hopping, right? So as you can probably already imagine, the diffusivity, which reflects really the physics or the mechanisms of diffusion, would be quite different from the interstitial case and the substitutional case, right? So this is something that we need to be focusing on. So the general framework, the general mathematical framework for the Fick's law still holds true, and the equation for diffusion is also true, but the diffusivity for these two different cases, namely the substitutional diffusion versus interstitial diffusion, will be different, right? Because they're based on different physical mechanisms. And we do see from the case of interstitial diffusion, how physics come into the diffusivity. So that is something that we're going to work on. Okay, so now if we take a look at the diffusivity that we first work out for the interstitial diffusion, this is what we get, right? In the homework, I think we'll have a better understanding of the meanings for each parameter, but in here I'm just repeating. So the alpha is the interatomic, the distance between two successive atomic planes where the atom is hopping, right? So basically, you have a plane here and you have a plane here. So this distance is basically the parameter alpha, okay? And this gamma is the hopping rate, okay? It's the number of hops this guy gonna make per unit time. So this is a hopping rate. And the factor 1/6 is because we're just looking at one particular direction. So, but this is generic, right? This is still holds for both interstitial and substitutional diffusion. And we also see that this geometrical parameter, which tells you the interatomic distance, we can easily change this to whatever the lattice we're working on, right? The key thing that absorb all of the things that we need to work with is this hopping rate, right? Because the mechanism how an interstitial particle hop into a neighboring site, and the mechanism how a substitutional particle hop into a neighboring site is different, right? In this case, for the substitutional case, we have to wait for vacancy. So we'll probably see that's going to be where the difference come from. Okay, so we're going to work out this guy in detail, this hopping rate. Okay, now keep that in mind. Okay, so let's first look at what is the hopping rate for the interstitial diffusion, right? And then we're going to see how we're going to generalize this. What are the quantities still remain the same, and what other quantities are different? Okay, so here I'm listing the hopping rate for the interstitial diffusion, and in those cases we use B to denote the diffusing particle. In here we use A, right? So this is a distinction. And this is a hopping rate that we all kind of agree on and work out together, right? So, and this Boltzmann factor, okay, which is an exponential function of this energy barrier over the thermal fluctuation. We know this is characterized the basically the energetic consideration of the system, right? So we have some the kick or the driving force for the hopping going to come from the thermal fluctuations. You get a large enough energy and to go through this barrier, because in the case of interstitial diffusion, we know the atom has to squeeze through a pair of tightly packed parent atoms, right? And this is going to cause energy, which is given by this delta Gm, right? And this energy, the energy going to be, where are you going to get energy to go over this barrier? Or the energy that you get is from the thermal fluctuations, which is characterized by this RT term. So this is a Boltzmann factor, okay, characterizing that aspect. And what is Z? Do we still remember for the case of interstitial diffusion? This Z is the number of available sites, right, for that interstitial atom to hop into, right? And V, oops, okay, or sometimes this is nu or whatever. So this, we call it V, is the vibrational frequency, right? So each atom is just vibrating around, and at some time it can receive a large enough thermal fluctuation to go over the energy barrier, and then this atom can hop into the neighboring sites, right? And Z is just the number of sites available for this interstitial atom to hop into. Okay, so now here's an interesting question. If we want to generalize this equation for the hopping rate from the interstitial diffusion case to substitutional diffusion case, mathematical wise, okay, what term we need to keep in there and what terms we need to modify? So if you look at this mechanism for this substitutional diffusion, do you think there's still a activation energy required for this guy?
No.
But in order to move it from one place to another, I think there is some energy should be required.
There is still some energy, right? So if you think about this scenario, okay, this is, I think, easy to see. In the case of interstitial, we know the energy barrier mainly comes through, squeezing through these two guys, right? You have to, squeeze through two tightly packed atoms.
I think Z will change. I think the number of available sites will be different.
Yeah, but let's first analyze each term in order, right? So the activation energy for the case of interstitial comes from, you have to go through a tightly packed pair of atoms. So this is going to cause electron clouds of the interstitial atom to overlap with these two guys and cause an increase of energy, right? So that's where the activation barrier come from. But in the case of substitutional particles, right? You think about initially, look at this guy. Okay, it has probably a very well-defined bonding. In this case, maybe metallic bonding with these neighbor atoms, right? So they're happily sharing the electrons. So it's in this equilibrium position. Now, if I have to pull this guy away from this equilibrium position and all the way through, what I have to do effectively, what I have to do to the initial bonding?
You have to move
to break it.
I have to break the bonding, right? So I know that when two atoms form bonding, this is going to lead to a low energy state, right? Because their electrons are happy, they find a new state with lower energy, mutual lower energy, right? So when I break these bonds, what does this to the energy? So if I pull this guy halfway right here, I break the bound. So this means that I increase the energy of the system, in particular, increase the energy associated with this particular atom that are moving. That makes sense to everyone? And when this atom make the hop, sit back into this location, it may form new bonds with all of these new neighbors, and then it's happy again because the energy is going back. So if you think about this, are we going, if we think about the hopping processes, we're going through the similar, energy landscape, right? Initially, we're happy with bonding, and then if the bond is breaking, we have to increase the energy. And then when we form the new bonds, the atom is happy again, right? So these two correspond to the local sites that this particle, can happily stay. And this is the energy barrier that, if you do the hopping processes. Does this make sense to everyone? Okay, so in general, you see that the mechanism is different, but mathematical wise, there's still a non-zero, generally fairly large activation energy associated with, this is associated with the process of hopping of this atom from this side to that side, right? But mechanism is different because here it's more related to the breaking and forming of bonds. In the case of interstitial, it's mainly due to the overlapping of electron clouds. Okay, but still in general, you're going to have the energy barrier, right? So we know that, okay, in general, I have this term kept, but the form or the value of this energy barrier clearly going to be quite different from the interstitial because the mechanism is different, right? But we do not worry about those quantum mechanical details. We just need to know, okay, we can definitely need to keep this Boltzmann factor, okay? So, and next, let's look at this vibration frequency. Now, clearly, this atom is also moving around, jiggling around, right, at any finite temperature. So you're definitely going to have this vibrational frequency, right, back into the picture. So, and also, now this is also important. This is a geometrical quantification for the local configuration of the atom, right? You have to have some available sites in order for this guy to hop into, otherwise you didn't have any diffusivity, right? So we from the previous slides, we also conclude that if you have a perfect nanocrystalline material, very small single crystalline material, there will be no diffusivity, right? And if you look at mathematics, what is the factor that gives you no diffusivity? We're definitely going to have non-zero alpha. We're definitely going to have non-zero Boltzmann factor for any finite temperature. The variation of frequency is large. So the only zero factor is what?
Z.
Is Z, right? Because there's no available sites. Does this make sense to everyone? Okay, so you know that, okay, this term is something that we have to modify a little bit, right? So in the case of interstitial, we simply use, the number of available interstitial sites or simply the coordination number associated with these holes in a crystal structure, which we're going to work out through the homework 1 problem in detail for the FCC. But we know in general, in the interstitial case, this Z is independent of the concentration of the diffusing particles, etc. It's just a material property, right? But in here, what are difference from the substitutional case? In here, Z, okay, clearly going to be a function of your crystal structure, right? So if I have the simple cubic, and this is a very simple two-dimensional simple square lattice, right? So I know that, Z going to be related to the actual available neighbors, right? Maybe in here, I'm just listing 4 nearest neighbor, right? So it's related to the coordination, right, of the crystal structure. But there's another very important factor contribute to the actual number of available sites, right? So what is that additional factor? We know in here, the coordination number, look at this, right? The coordination number is 4, right? But what is the available sites?
1.
Only 1, right? So this is a vacancy. This is only 1. So we know that, okay, we're going to have something here. Still, this is available sites, but this available sites is going to be related to both the crystal structures through the coordination number, and it's going to related to a fact, to a factor that is going to convert this coordination number to the actual available sites, right? So that is something we need to work out. And what do you think that is the factor that can convert the coordination number to the actual available sites? What is the
concentration?
Vacancy concentration, right? What is the probability that any randomly selected site is a vacancy, is an empty site, right? That makes sense. So basically we have 4 coordination number here, right? But we know that it's only going to be, very small probability that one of these coordination number is a vacancy. And that probability is the probability of any randomly selected site is a vacancy site. And that is by definition, the concentration of vacancy. Okay, so let me show this in the next slides. And this will be clear. So yes, this is something that we need to change, right? The number of available sites. And then if we move on, okay, as we said before, so I'm just listing these, but here is the key, right? So now I'm trying to work out the hopping rate for this substitutional case, right? And as we analyzed before, we keep the Boltzmann factor case. This is a free energy barrier for the hopping. We know that, come from a different physical consideration, but you still have this term. We have the vibrational frequency. Again, it's depending on different type of atoms, but we still have them here. And these two terms together, okay, let me do this. So these two terms together, okay, gives you the number of available sites, right? So it's not only a function of the coordination number, which is the Z. Okay, you have to take the coordination number and multiply the vacancy concentration. So this gives you that out of this Z number of neighbors, how many neighbors on average going to be a empty site, so that I can hop into that empty site. And this XV is vacancy concentration, which is the probability that a randomly selected position or atomic site is a vacancy site. Okay, that this makes sense to everyone based on our analysis. Okay, so I think it's quite clear if we went through this processes, right? So you see here, this is again, we see how the actual mechanism for diffusion come into this picture. Mathematical wise, we still have the Boltzmann factor, the vibrational frequency, coordination number, but in the case of substitutional diffusion, we have to multiply the whole thing by the vacancy concentration, right? Because that's going to give you the actual number of available sites to hop into. Okay, so now without going into the next slide, let me just ask you this question. Now, in general, if we compare, okay, if we compare the rates of diffusion, or in general, the diffusivity, right, of a interstitial diffusion and a substitutional diffusion, in general, which one do you think is gonna occur on a faster rate?
Substitutional, depending on the vacancy concentration. The faster will be substitutional. Right?
So is the vacancy concentration a value larger than 1 or smaller than 1?
Smaller than 1.
It's smaller than 1.
It's smaller than 1, right?
Smaller
Is,
than
is, is that close to 1 or much smaller than 1?
Much
It's
smaller.
Much smaller than 1.
It's much smaller than 1, right? Because you have a solid material, and this material typically we consider is far away from melting, right? Even you're very close to melting, you see the concentration of vacancy is still very low, right? So at room temperature, we will show estimate, or we'll show equation for this, but the vacancy concentration is very, very, very small. Okay, it's easily can be 10 to the minus, I don't know, 20 something or 15 something. Okay, so it's going to be very, very small. And then basically now what do you have? You have, if you didn't have the vacancy concentration, you have the hopping rate for a normal substitutional interstitial diffusion, right? And now you have to multiply a very, very, very small number to this hopping rate. So what are you going to end up with? A very small diffusivity, right? In general, a very small diffusivity. Of course, there are other things that will be different, but in general, you see that this vacancy concentration is a very, very small factor that's gonna significantly bring down, your diffusivity, right? Again, I emphasize there are other factors, but at least you see that in general, because of the fact you have to multiply a very small vacancy concentration to the hopping rate for the substitutional diffusion, the substitutional diffusion is generally much slower than interstitial diffusion. Again, this is a general. There are cases where substitutional diffusion may be faster, but in general, okay, this is the role that played by this vacancy concentration. Okay, so now we have a fairly good intuitive understanding of this. Let's move on to see what is the in detail, what is the effect of the vacancy concentration in terms of the mathematics to this hopping rate and diffusivity. Okay, let's move on. Okay, so now one thing is that, which I cannot show you this again, I'm relying on the previous material class you're taking. So we know that in thermal equilibrium, the vacancy concentration can be generally written in this form. Okay, so this is not quite rigorous. I'm ignoring some constant, but in general, the vacancy concentration is proportional to a Boltzmann factor, associated with a activation energy to create a vacancy and over the thermal fluctuations. That this equation makes sense?
Yeah.
Okay, so what is activation energy? Think about this, okay? suppose that originally have an atom right here, right? And if you want to take this atom away from the system, what do you have to do? You have to pull this atom, right? Because they're all metallic bonding initially, and you have to really pull the atom out of this picture, right? And when you pull this atom out of picture, what do? You do work, right? You do work to the system. Does this make sense for everyone? And if you put atom, away from the system to infinity, and then this, because you do the work, this is basically you create a vacancy, right? When the atom that you pull out from the system is very far away from the material, you can consider this as an independent atom, and in the material create a vacancy. But during this processes, you do work, right? And that work can add energy to the system, and that work is basically this activation energy to create a single vacancy. Does this make sense to everyone? Okay, so this is where you have the activation energy for the vacancy. Okay, but in general, in real materials, we're not pulling the atom out, right? And it's the thermal fluctuations, is the thermal energy, the kinetic energy of the atoms themselves can actually kick them out, because if you have an atom here, at some time it receives a huge kinetic energy, you're going to escape from all of the potential energy traps and become a free atom and leave the material. So this is the where's the actual driving force for forming the vacancy. And in thermal equilibrium, these two balance one another. Okay, so that give the Boltzmann factor between those two, going to give you rough estimates of the ratio among all of the atoms, how many can become a vacancy. Does that make sense to everyone?
Yes.
Okay, cool. So, and here I want to say a few more things. Okay, so I think this is kind of interesting, which is not directly relevant to diffusion, but it's since we talk about a vacancy. So do you think vacancy is, is in thermal equilibrium? Is these guys, really favored, or do you think that these vacancies are equilibrium defects or they're non-equilibrium defects? Which means that, are they really thermodynamically favored? Because, as we can see, if you create a vacancy, you increase the energy of the system, right?
Yeah, no, they are not.
They are equilibrium defects because we are also increasing the temperature and vacancies are favored.
So, this is an interesting question, a way to answer that. So if you look at that, whether these vacancies are equilibrium vacancies or non-equilibrium vacancies, what is our rule? What is the evidence to demonstrate this? I think the evidence is that these vacancies are observed at all temperatures that above zero, right? Absolute zero. And the increase in terms of number will increase temperature, and they're stable in there, right? So if these are non-equilibrium things, so what you do is that you keep the temperature high, and these vacancies should go away. Does that make sense to everyone? Like the green boundaries, right? We know these green boundaries are non-favorable because it costs high energy. So if you have a polycrystalline material with very small grains, right? Many small grains with a huge green boundary area, and you put this material at high temperature, you wait for a sufficient long time, what do you see? Do you see increase of green boundary or decrease of the green boundary?
Increase.
You see a decrease of the green boundary, right? You see the grains grow larger and larger. Does this make sense, or is this something new?
Yeah.
Okay, right. So this is an issue why people that they know that we know that if we make the grains very small, they're going to have very strong mechanical properties, right? Because dislocations are going to be stopped. There's a lot of good things about nanocrystalline material, but the challenge here is that they're not stable, right? You use it for once, or you put at high temperature, all of the grains become larger and the material properties degrade. So this is a huge issue in engineering these nanocrystalline materials. So people invent different ways to pin down the grain boundary so that it can be stable. So we know that the grain boundaries are non-equilibrium defects, right? Because if you give the system sufficiently long time to equilibrate, these guys eventually going to go away, right? If you wait sufficient long time, all the material going to recrystallize into a single crystal. Ideally, right, in principle. So we know that green boundaries are non-equilibrium defects, but how about a vacancy? The vacancies are equilibrium defects in the sense that, you increase temperature, they increase. If you keep the temperature there forever, they're gonna still stay there forever. They're not gonna decrease in number, or they're gonna gone, right? So we know as a fact, they're equilibrium defects in this sense. But the answer is, the question is why? if you lose energy, right? If you lose, you have to do work to the system to increase the energy. What is the gain? By introducing vacancy. What are the major contribution to the free energy of the system? We talk about thermodynamics. I know we've been talking about diffusion for quite a few lectures, but we cannot forget thermodynamics, right? When we talk about the phase transformations, we analyze free energy of change or free energy of mixing. What are the two different terms, the two contributions that we typically analyze or work with for the free energy?
Enthalpy and entropy.
Enthalpy and entropy, right? And here, by say increasing the energy, by doing work, by breaking the balance, what we're changing here? The enthalpy term, right?
Enthalpy.
This is the interaction between the atoms, between these guys. But how about entropy? If I introduce vacancy, do I introduce entropy?
It's increased, right?
Yeah.
Yes, right? Because if you have a perfect crystal, how many configurations do I have? If I have a perfect crystal,
One.
one, right? We do not consider vibration, just look at the configuration, atomic configuration. You have just one, right? Because it's perfect crystal. But if you have a vacancy, how many configurations you can have for this one vacancy?
We have a lot of configuration.
So
If you have n atoms in the system, if you have an n atom system, you have n configurations, right? Because
configurations, yeah.
any atom can be a vacancy, right? And you can see that this increase factorially fast if the number of vacancy increases. Does that make sense?
Yeah.
Okay, so basically what you have here, why vacancy is equilibrium effects, and they're favored at high temperature because they increase the entropy of the system, and through that they stabilize the system. And they actually, this is a mechanism why you have, melting is inevitably related to this vacancy concentration, right? You have sufficient vacancy concentration, you basically fluidize the whole material. At high temperature, have more and more vacancy, and then this whole material kind of basically, lose connectivity, and then to become a fluid. But anyway, that's a different thing. So yeah, I just want to quickly mention this is a good review of the thermodynamic aspect, but this is a vacancy concentration, okay? And now what we need to do, or what we can do is that we can combine these two, right? Let's go back to the diffusion. So this is the hopping rate, right? We know that the only thing that we need to take into account additionally is this vacancy concentration. And from thermodynamic considerations and from other classes we already learned, we know that this is the, a good way of describing the vacancy concentration. The reason why you see this is typically very small is because the activation energy is usually high compared to the temperature you're working with, right? So at room temperature, at most normal temperature regimes, this vacancy concentration is very small simply because this delta GV is very high. You have to pull this atom out of the original position, right? You can imagine you have to do a lot of work. So yeah, that's the factor. So now what if we combine this vacancy concentration and with the hopping rate that we work out? Okay, so you basically gonna work, basically you combine these two exponential term together, right? And you see that's why you're gonna have a much lower value for substitutional diffusivity compared to interstitial. So, if you plug this back in here, you see this part, the first three, the four terms will look exactly the same for as in the interstitial case, right? We have the interatomic distance, coordination number, and this vibration frequency. But the Boltzmann factor, this exponential form, you'll see that we have a huge increase of activation energy, which take into account also the energy barrier for creating a vacancy. Okay, now this is another way of looking at this, diffusivity for substitutional diffusion that is much smaller than the interstitial, because the energy barrier is increased a lot, because we have to consider the creation of vacancy as well. Okay, and then once we understand that, I think this is pretty straightforward. We can also write down the contribution to the free energy difference by creating vacancy in terms of entropy contribution versus enthalpy contribution, etc. And eventually you can still write down the diffusivity in this particular form, right? You can write this as a temperature independent constant, and then you have this Boltzmann factor, and within this Boltzmann factor, you have this effective activation energy, which is only taking into account a temperature dependent enthalpy term. And here you have the thermal fluctuations. And for the independent part, you have this thing, okay, which is also very similar, but you have to add the change of entropy due to the creation of the vacancy here. Okay, so that's basically the substitutional diffusion. Okay, so again, the take-home message is that I think the whole thing here is to show that you can actually use the same trick to also measure the substitutional diffusion as we did before, right? If you do, the diffusivity measurement at different temperature, you can do a interpolation as a straight line if you take the logarithm of these two, and you can estimate these different parameters of D naught and QSD. Okay, so but the key thing here is to realize that the key difference between the substitutional diffusion and interstitial diffusion is that the substitutional diffusion have to involve vacancy, and that's going to significantly reduce the actual diffusivity for the system in general. Okay, so this is substitutional diffusion, but other than that, all the mathematics are the same. All of the tricks we use to measure diffusivity are the same. And most of the physical considerations are also the same, right? The only thing is that we have to take into account vacancy. Okay, that's that. Okay, so now let's look at another interesting scenario, right? Because in here we spend, most of the time analyzing the substitutional diffusion by focusing on what? I'm focusing on this particular real atom, right? So, and only in this case, when I hop into a neighboring site, I need to worry about the vacancy because I have to make sure the site is available for this real material to hop into, right? And we mentioned before that equivalently, we can also look at this process as a diffusion for the vacancy, right? If you imagine that the vacancy is an imaginary particle, right? We can focus on this particular particle and see how this particle move around in the system, because that's the same process of the substitutional diffusion, right? We're just focusing on the vacancy. It's like in semiconductors, you can work with electrons or work with holes. That's the same thing. Here, we're just working with the vacancy, right? So now let's see, so the interesting thing is that, if we work with vacancy, in general, or ideally, we should get exactly the same results because we're describing the same processes. But we'll see there's apparently dilemma, which is quite interesting for us to work with. Okay, so let me see. So in here, I just summarize all the results we have, right? So this is for self-diffusion, right? I just listed the diffusivity I derived together with you guys, right? And then let's move on to the vacancy. So here I use dV to distinguish the vacancy diffusion or diffusivity frequency. But again, you see that if we consider this is an imaginary particle for the vacancy, right? And it's also going to move in the same way that a real particle is going to move. So this wouldn't change the interatomic distance. This alpha is the same, right? It's the distance between these two atomic planes. And then we see that all of the key tricks we can play is going to be in this gamma V, which is a hopping rate for the vacancy, right? And we do the same thing because the vacancy, if you look at what is the activation energy barrier for the vacancy, that activation energy barrier is going to be exactly delta GM, right? Because you're not moving the vacancy, you're actually moving your atom, dragging atom back into this vacancy. So those two processes are going to have exactly the same activation energy. Does this make sense to everyone? Because that's the same processes, right? So vacancy itself is not a real material particle. It has no energy at all. But if you look at the processes, right, this processes is the same as a single particle hop into the vacancy. So a vacancy hop into a available size is equivalently have the same activation energy for that, right? So we have this. But what is this a number of available sites? If you look at vacancy, look at this guy right here. What is the number of available sites?
1.
1 or Z, where Z is a coordination number. If we consider low concentration of vacancy, so we consider that for each particular vacancy, all of the nearby atoms are real material atoms. What's going to be the coordinate or the available sites?
0.
So clearly it's not 0, right? If it's not 0, this means that the vacancy cannot move around. And we know that the vacancy diffusion and the atomic diffusion is the same processes. So this is non-zero, right? It has to have some diffusivity for the vacancy. So if I'm a vacancy right here, can I hop into this guy? Or if I'm vacancy right here, let's look at this. Can the vacancy move to the left and take up this atom position? Yes, right? This is what happens here. Can this vacancy go up?
Yes.
Yes, right? Can this
Yes.
vacancy go to the right,
Yes.
Yeah.
to the down, to this? Yes, right? It can
4,
take,
I think.
it can eat up any real atom and change position with that atom, right? Because all of these sites are available sites to this vacancy. Does this make sense, everyone? Is it physically clear? Let's do not think about dilemma. I'll solve that later. But is this process physically clear?
Yeah,
Yes. Yes.
Hello, can you still hear me?
Yes, I can hear you.
Yes.
I'm sorry. I think my network connection was lost for quite a few minutes. Good, we're back. So let me continue. Let me see. Are we here or not? Let me see. Yes, we're working with the vacancy diffusion, right? And you know, one interesting observation that we have is this Z, okay, is the coordination number, right? And all of the other parameters are the same for the substitutional diffusion. So this you know, and everything we work out is correct. So there's nothing wrong with it. And then this basically, you know, leads to a very interesting observation, because if you compare the diffusivity for the vacancy and the diffusivity for the actual material atom, you see that these two differ by a huge factor of the vacancy concentration, right? So because in here, if you compare this to, you know, in here I have a vacancy concentration multiplied to get the diffusivity for the material atom, but for the vacancy itself, I don't need that factor. So these two are differ by a huge factor of the vacancy concentration. Does that make sense?
Is the capital V for the vacancy diffusion subscript, is that the same thing as the new?
Yes, it's the same thing. I'm sorry, this is my typo, but it's the same thing. It's this dV supposed to be V is the vacancy diffusivity, right? If you
Okay.
compare the vacancy diffusivity is much larger than the diffusivity of the real atom, right? Because you have to divide the very small factor. But the dilemma or the question that I want to ask you is, you know, we know from a fact that the vacancy diffusion and the atom diffusion, they're basically the same processes, right? We just choose to select the different you know, particles to track to analyze this, you know, using the same mathematics, but why can get quite two different dynamic rates for the same processes? That is the question that I wanted to ask. Is that clear, or that this the question clear?
Yeah, I think the question's clear.
Okay, yeah. So because I wanted to give you some time, because we wasted quite a few minutes. So I just want to show it here. So now essentially, you know, let's look at this very simple picture, right? And clearly, you know, we focus on this particle, right? This is a vacancy, and we clearly see this vacancy is diffusing around. And that is clear, right? So we know this has fast diffusion. But when it comes to the particle diffusivity, what we're talking about, right? When we talk about particle diffusivity of the real atom, say we randomly pick a particular atom, right? For example, this black one, if you can see what I'm showing here. So let's pick this black one. This black atom is not a different atom. It's just to show that you have, you know, a substitutional right here, right? We're interested in the diffusion of this particular guy, okay? And we know that, okay, the vacancy diffusion is fast, right? But each time this vacancy gonna involve a different atom. Does that make sense to you? But when we talk about atom diffusion, it's the same vacancy, right? So it moves all the time. But each time this vacancy gonna involve a different atom. So if you look at it from the vacancy perspective, it does move very fast, you know, from this animation. But how about the atom? Okay, if you look at this atom right here, you know, during the very long range diffusion of this whole vacancy, the atom does not change position at all, right? And if it were change position, it has to wait until this vacancy before it's annihilated by this guy, move around near this particular atom, and then it can hop into the vacancy. And this particular atom only move once, even if the vacancy is nearby, right? But before the vacancy can move to this atom, the vacancy already moved for a very long, you know, distance by doing many hops. Does this picture make sense? So if you look at these two guys, right, these atoms, you start vacancy from here. So, right, and then you see this guy first move, right? And then the vacancy move on. But if you focus on this guy, it only does one hop for all this time, right? Well, the vacancy, you know, did a lot of hops to go from the original position to all of these positions. So if you look at this guy gonna move in a much slower rate, right? This guy, compared to the vacancy, it does move once, and then it's gonna stay there. And for the, you know, the simulation, it's gonna stay there forever. Does this make sense to you? So this means that, okay, vacancy and atom self-diffusion, they're the same processes, but if you look at a vacancy, it does apparently to be moving much faster, right? Because it moves all the time. But if you come to the particle, it's not, right? It only moved once and they're gonna stay there and wait for another vacancy to come nearby and it can move again, right? So this explains the difference of the apparent diffusivity. Because when we talk about diffusivity of atom, you have to focus on a particular atom, focus on this guy. Say I can use radioactive, or some other tracers to keep track of this atom, right? And this, it involves in the motional vacancy only once and it's gonna stay there. So, if I keep track of this atom, I have to wait until the next vacancy comes nearby and it can move. So it will move much slower, but the vacancy is moving all the time. Okay, so hopefully this is gonna explain this dilemma. So still, there's no contradiction here, right? They're the same mathematics describing the same processes. Okay, when you focus on vacancy, of course, it moves faster because it's always going to be moving. But if you look at a particular atomic particle, it can move involved in one vacancy movement, but after that, have to wait for a very long time until the next vacancy comes nearby. So that's where the vacancy concentration come into the picture, and that's also the reason why the atomic self-diffusivity, the diffusivity going to be much, or substitutional diffusivity going to be much slower than the vacancy, although they're the same processes. Okay, so after that, I have to move on. Yes, that's basically the observation. I have to move on and quickly mention one interesting observation analog between the thermal diffusion and this mass transport and thermal transport, right? So I will not go through this in detail, but I just want to list the similarity or point out the similarity in terms of their mathematics. So in the case of diffusion, we work out the Fick's laws, right? And it turns out that we have a very similar relation between the heat flux and the actual temperature of the system, okay? Again, I will not go through the derivation, but I think this is going to be including any thermodynamic classes or textbooks. If you're interested, you can go to those, refer to those references. But this is the analog of the Fick's first law. We use the lowercase q to denote the heat flux, right? The amount of heat that passing through a specific unit area per unit time. And this is proportional to the temperature gradient of the system. And the constant proportionality is what we call the heat conductivity, right? And also you have the local conservation of the heat. T is the temperature. This only tells you, it's an effective parameter to describe the amount of heat in the system, because you can easily times the heat capacity to the temperature, get amount of heat in the system, right? And the heat is not being created, it's not being destroyed. We consider the rate of change of heat or temperature is simply due to the flux. Now, under these two conditions, which is typically true in most material application, you can obtain the so-called heat transfer equation, and we'll see that it's exactly the Poisson equation that we already worked with for the mass transport on the diffusion, right? The only thing that you can change the concentration profile of the concentration field, replace that with the temperature field, and also you replace the diffusivity with the heat conductivity, right? This is the transport rate or transport parameter for heat transport. Okay, so I just want to quickly mention that. So all of the solutions that we mentioned about solving the diffusion equation can immediately apply to the heat problem, and all of the homogenization of density fluctuation can also be applied to the homogenization of temperature fluctuations, and also you have this exponential decay for a initial high temperature region, over long distance, etc. So all of these holds, and we're gonna use some of these results in our subsequent analysis when we talk about phase transformation, because we're gonna worry about both, temperature profile in the material system and also the distribution of solutes. Okay, but I will not go through the mathematics for this. It's out of the scope. Okay, so that's all I want to say about diffusion. Okay. Here is the brief summary for I think the last two lectures we have discussed, and we have went through this list a lot of times, so I can skip this. Okay, so I hope that this is clear for the diffusion. Now, let me quickly share the homework with you, because last time I got a lot of feedback concerning the homework, so I think it's worth the time to go through some important aspect of homework in the lecture, so we're clear, at least, we're clear on what we should be thinking in here. So this is about, the first question about the diffusivity, right? So about physical interpretation of diffusivity, and we know that we can make a connection between the hopping rate to the real physics of the system, right? In here, I just want you to apply that equation, which may be very abstract, right, to you when we first talk about it, but do this practice so that equation can be now more intuitive, and you know that how the relation can be established. Is this question clear? We just need to do this calculation for the FCC iron, right? For the carbon interstitial diffusion FCC iron. And the equation we're going to be using is this diffusivity, right? So this part is what we call D naught, right? And this part is the temperature dependent thing. And in this class, in this particular problem, we didn't have to worry about this guy because I give you the value for the D naught and I ask you to estimate the vibrational frequency, right? Let me see. Yes, this V right here. Does that make sense to everyone? Okay, and I give you assumption that this delta SM, this enthalpy of mixing or enthalpy of due to diffusion is 0. So if you plug this equals 0 in here, what do you get? What is the value for this factor?
1.
It's 1, right? So and then it's very straightforward. So basically, this is a D naught, and if you have this equals to 1, so what do you have for D naught? At 1/6 times alpha squared times Z times V, right? And what you're looking for, you know D naught, right? I think I gave you D naught. Did I? Or not? I think even if I didn't give you, I think this can be easily find out from the references, textbook, and if you do Google, this can be easily find out. But this is something you know, right? D naught is something you know, right? And V is something you're looking for.
Professor,
Yes.
I have a question. So in interstitial diffusion, why don't we consider the concentration of interstitial atoms?
I'm sorry, can you say that again? Can you say that again?
In interstitial diffusion, why didn't we consider the concentration of interstitial atoms? So the number of sites, available sites will
Oh,
change.
because we always, in the interstitial diffusions, we always consider, we have a low concentration of the solutes of this carbon, right? If
Okay.
and so the chances that they run into each other is very low. But that is assumption. We're just using a first order assumption. So you can actually have corrections to this. But if you have corrections, you have corrections with respect to Z, right? This is going to be a function of the concentration of the atom, right? It's Z times 1 minus roughly the concentration times the constant. This is first order correction. Now we're considering a 0 order approximation, thinking that the concentration is very low. Does that make sense to you? Yeah. Okay.
Yeah.
So.
But concentration of vacancy also was very low, right?
No, in here we didn't have worry about the vacancy because we only need to worry about the number of sites, whether this can hop into, right? And the only case that a site is not available is when there's another atom, the same atom taking this position, right? So this is gonna lead to a reduce of Z. So now your Z star gonna be Z, right? This is the original coordination number at a very low concentration times 1 minus something, right? And in the first order, this is going to be A times X, where X is your concentration. And you're going to have higher order corrections, which we'll never consider, right? So this means that if you have, the concentration is low, but not that low, you're going to have a correction, effective reduction of the available sites proportional to the concentration. But now we even ignore this term. We only consider 0th order approximation, which means X is very small. Okay. Okay. So yeah, this is going to 1, right? It's not going to be relevant. This is something we're looking for. So and this is what we know. So the only thing that we need to work out is what is alpha and what is Z. Does this make sense for everyone?
Yes.
So this boils down to a crystal structure problem, which I like a lot. I think will be very helpful. So what structure do we have here? We have FCC, right? Let me clarify this. Go back. So FCC, this is FCC, right? So, and we're talking about interstitial sites for FCC. And where do you think are those sites? Can we see this?
Sites.
These are octahedral sites, right? Can we see this is FCC cube? Can you follow the lines? You see this is a cube, right? And I didn't highlight all of these things. The nodes here are the supposed to be original atom, the iron atom, right? And it highlights a small group of them, and this one is a carbon atom, which is right in the middle of the octahedral, right? So the FCC structure is basically a collection of octahedral and tetrahedral network, and the interstitial sites for carbon are these octahedral sites. Does this make sense to everyone?
Yes.
Okay, so now if this is clear, then it's very easy for us to compute. What is alpha? Alpha is the interatomic distance, right? So if there are multiple ways you can see that, but you see this is one side, and here, okay, you see this is another octahedral cage, and I can see the next position that it can hop to is right here. Does that make sense to everyone? So, and I can say this is one atomic plane, and this is another atomic plane, and then this is going to be the distance between the two atomic planes. Is this clear? Okay, I have to assume this is clear. So what is this distance? If the original lattice vector, the lattice parameter for the cube is A, and what is the distance of this guy?
A by root 2.
The distance of the guy is this guy, right? This guy is square root of 2 divided by 2 times A, or A divided by square root of 2. That's the same thing, right? So that's your interatomic distance. So I'm effectively solving the problem for you. Okay, is that clear? Okay, so this is quite straightforward. But what is, so we know this A or alpha now. So what is the coordination number? That's, I think, a little bit more trickier.
For FCC, it's 12, correct?
Yes, but for FCC it's
eight.
12. But you know, I want to know the reasoning, because for FCC the 12 is okay, but the 12 is typically associated with the nearest neighbor for this real atom, for the atom on the sides. But how about the atoms in the interstitials, right? So that's what I'm asking. But the answer is correct though. So the way that you can look at this is that, let me move back to
Professor,
continue.
it's the number of available sites, right?
It's the number of available sites for this guy, right?
Not the coordination number.
Not coordination number, but the number is 12, right?
Coordination number is 12,
But
the number of available sites is not 12.
it is also 12, right?
It's 8, right?
No, it's 12, because so
It can move to like 4 on the same plane, like on the horizontal plane.
it can move 4 on the same plane, right? And,
And it
four
can move
4
4
in
on
the
the-
above and 4 in the below.
Yeah, so it's 8.
No, you have 4 in the plane and 4 above and 4 below. So it's 3 times 4 is 12, right?
Can you show the below how it is 4?
Well, the below 4 is the same as the above 4. If you see the above 4, you see the below 4. Because they're symmetric.
Here is the center atom. Okay.
Right? Because you know how we see this, I think the easiest way to see this is that you see that if the atom is making a hop, right? What it has to go through? It has to go through an edge. Does that make sense to you? Right? Because it has, you know, if this atom is making a hop, it has to squeeze through these two densely packed atoms. So it goes through this edge. Does that make sense? Right? So it has to, you know, if this guy is hopping from here, hopping from here to here, it has to go through this edge, right? And if hop from this to this side, it goes through this edge. And it goes through this edge and it goes through this edge. Does that make sense for everyone? Okay, and octahedral, so basically this means what? This means that this atom is in octahedral cage, right? And if I want to hop into a neighbor's size, what I have to do, what is the only way that I can escape from the cage? I'm showing that you have an atom here, so you can basically escape from the cage through this 4 edges, right? But every single edge of this system is kind of equivalent, right? If you look at this edge and these edges, you know, these are the same. So each edge corresponds to a pair of densely packed atoms from which the particle can be able to squeeze through. So the number of available sites is simply given by what? The number of edges you have for an octahedral cage, right? Does it make sense? Or?
Yeah.
So, and how many edges does an octahedral have?
12.
12, right? So that's basically how you get Z. Okay, and if you have Z and alpha, you have to, you know, find out what is A for the FCC iron. So that is something I leave to you. You can easily do this from Google or go back to your material science engineering introductory level textbook. You should have those information and plug this back in. You should be able to estimate what is V. Okay, and you should get a sense whether this is correct or not, because you can get order of magnitude of vibration frequency, right? And you know that these atoms typically vibrate like crazy, so that's going to be a huge number. Any questions?
Can we take the value of D naught to be 2 as it is given in the question?
Yes. Or if you have a better value, that's also welcome. This is kind of an easy number I give you, so you can do a fast estimation. Okay, so now if this is clear, right? I think this is probably the most trickier question for this homework. The others will be very straightforward, but let me still discuss this. So this one is, if you look at this one, thinking about solving the diffusion equation, and that's gonna be too much. Okay, what I'm only asking from you is to get a quick estimate of the time it requires if you increase diffusivity, right? So the basic idea is that you have a bar like that, and if you penetrate, you want to use some carbon to penetrate this bar, so you can attach the carbon to this end. As we described in the class, you can attach carbon to this end, and then the carbon going to diffuse in this direction, right? Does that make sense to everyone? Okay, and if the total length of this guy is L, okay, and we know this, we're going to set this X equals to L. This is roughly the time it takes for the carbon to fully penetrate this bar. Again, this is an estimate, but this is good enough for this class, right? And this is, I have two different temperatures that I can consider, right? I have a low temperature, I have a high temperature. And if I change temperature, what do I change? If you look at this equation, if I change temperature, what do I change? Did I change L? Is this guy? No. Did I change this diffusivity?
Yes.
Yes, right? So I change diffusivity, I do not change L. Now this means that time is changing, right? Now, if I increase temperature, do I increase diffusivity or decrease diffusivity?
You increase it.
Increase, right? Because diffusivity is increasing. It's a very fast, exponentially increasing function of temperature. So I increase temperature by a very small amount, only 50 degrees Celsius, very manageable. And you see that we're going to get a huge increase of diffusivity. And as a result, we're going to get a huge decrease of the time required for you to do the penetration. Okay, so that's basically what this problem is about. But I'll stop here. If I tell you more, I think this will be too boring for you to solve, but that's the idea. Okay, you don't have to go through the diffusion, original diffusion equation to solve about this problem in rigorous. You can just use this guy. Okay, that's good for me for this homework. Any questions about this one? Okay, if no, let's move on. For this one, okay. I think there's a typo in the original homework, and I thank you for those who point out. So the purpose of this one is to just go through some mathematical practice. So I did a derivation for you for the one-dimensional case, right, which only considers the flux in one direction. Now I simply ask you to generalize this to the three-dimensional case and see where you have this gradient operator comes from. Okay, so and to do this is quite straightforward. So in a one-dimensional case, we just need to work with the flux in the x direction. We call this Jx, which is a component of the flux in the x direction. And we take out what comes out from what comes in, etc. Get the difference, right? And we consider this is a very small volume. So what comes out, this can be written as a differential form, right? And things like that. And you can easily get this component, right? And you can follow the exact same procedure to do the y component and z component, because you have this orthogonal cube here. So all three components are going to work independently, and all of them are going to contribute to the change of rate, right? So it's very easy it's very straightforward to get this, and you see that this is the gradient operator times the flux, which can be a vector in three dimensions. Does that make sense to everyone? Okay, I think this is very relatively straightforward, and apologize for the typo. So that should be the correct one. So now this one, yeah, basically the same thing, right? This is a one-dimensional case. Yeah, I just put down, copied the same derivation I had in the slides, but this is very straightforward. So the second question for you, I think, does this equation also hold for self-diffusion? Why and why not? This is a more interesting question.
Yes.
So I can tell you there's no definitive answer for this. It's based on your assumption, based on your condition you provide for the system. Okay, do you want me to give you some hint, or you want hint, or you want spend more time on this one? So I can give you some line of thinking. So what is the difference between self-diffusion and interstitial diffusion?
It requires a vacancy.
The vacancy, right? And is vacancy always conserved or not? Because if vacancy is conserved, then this equation is going to hold true, right? Like all the interstitial particles are conserved. So this is definitely right. The assumption for deriving this is because within the small box, there's no diffusing particles being created and there's no diffusing particles being destroyed, right? That's the assumption. Is this assumption also true for self-diffusion? And we already point out there's a vacancy involved in the self-diffusion, right? So whether this equation is going to be hold or not, depending on whether the vacancy can be conserved or not. Does this make sense, this line of thinking?
Yeah, vacancy should be get conserved, I think.
Okay. That's if you think vacancy is conserved and your conclusion is going to be the equation will hold, right?
Yeah.
But is there any chance that vacancy is not conserved?
If temperature is changed, then vacancy.
No, we always consider temperature is the same.
Yeah, then vacancy should be conserved.
Are you right? Are you sure?
Eventually,
No,
an
no, no,
atom-
no, no. Yeah, because that interstitial atom took place of vacancy and it just fulfilled the vacancy. But we are not assuming any interstitial atom there, right?
No, you can. If you do not assume there are any interstitials, you can say the vacancy is conserved. But the whole point I'm asking here, and the interesting part is the intellectually, you have to specify whether you want the system to have interstitial or not, right? If the system have interstitials, well, vacancy might not be conserved. So this
Yeah.
equation will not hold, right?
Yeah.
So this, the whole point is just to give you some idea, and kind of motivate you to work out under what conditions, you can apply this equation to study self-diffusion. So if you're working with alloy with a lot of interstitials, but also self-diffusion, you know that you have to use this with caution, right? Because the vacancies might not be conserved, so the equations may not be right for self-diffusion. Does that make sense to you? So that's the whole point. So again, this also applies to the interstitial case, right? Because if you have interstitial and you have a vacancy, and if these two alienated with one another, you're losing interstitial as well. So that's basically give us some boundary conditions on to what extent you can apply these equations. But I'll stop here and I'll ask you to think more, okay? But that's the line of thinking anyway. And the last one is very straightforward. Yeah, this is basically the same equation, right? So I would not read the question to you, it's quite clear. But you see the only difference is what? In the equation, what we have is that, the boundary conditions equals 0 and we don't have this C naught here, right? And in those cases, we're only looking at the fluctuations. But in here, I have a constant concentration profile added. And how this will change your solution? Any idea? Okay, for the sake of time, I'll directly say the answer, not the answer, but line of thinking. So the whole point is that, this equation is a linear equation, right? The diffusion equation is a linear equation. We know this, right? Do we know this? This is a linear equation, right? So what is the property of the linear equation? If you have a solution, C1 is the solution for the equation, and I have a solution C2 is also a solution of this equation. How about C1 plus C2? Is this going to be a new solution of the equation?
Yes.
Yes.
Yes, you can easily plug this in, right? You plug, you can literally show that if you have two solutions that are, two different solutions, C1 and C2 are both solutions to the equation and boundary value problem, things like that, the sum of these two is also a solution to this problem. Okay, so based on this property, which I think you probably already use it in your other classes. So the whole point is that, then we separate this problem in two problems, right? So first we do a problem with very trivial solution, but satisfy these C naught, this non-homogeneous boundary solution, and this constant. So we just have a constant solution, which is here, and this one definitely satisfies this equation and satisfy the boundary condition, right? And then we plug this equation together, combine this C1 with the C2, okay? And we know that if we combine these two will also be the solution to the whole problem. And then the combination of these two can satisfy all of the boundary condition and initial condition very easily. But here you have to make sure that you choose the correct Bn, because I changed this to 8 pi over L. Okay, but it's just as simple as that. Okay, so the final solution you get is something like that, or similar to something like that. Okay, so in our class, in our original class, the axis is right here, going through this average value, right? You have 0. You're just doing the fluctuations around a 0 value. But in here, effectively, what this does is that it can increase this a little bit higher to C0, right? So you're just fluctuating around C0, but when everything is converged and have no fluctuations, you just converge to a constant concentration profile C0. Okay, so that's all for the homework. I know that I already have 1 minute beyond, but I still want to spend some time to quickly go through the exams, the not exam, but the some of the ideas for the exam. So this is for the midterm exam. Okay, I'll post all of this information also on Canvas announcement. But after consulting my colleagues who have very nice experience with teaching these classes via Zoom, I think the best way for the exam is to do a take-home exam. So this will make all of us less stressed and probably focusing more on the real interesting stuff, right? So we'll do a time-limited take-home exam. Okay, so we're gonna do a 75 minutes exam because this is consistent with the length of the lecture, but I'll give you a 2-hour window. Ideally, I'm thinking from 10 a.m. to 12 p.m. Because you need to take the solution, print out probably the exam and work on the paper, scan this and send everything back to me. So I'll give you extra, some time to do all of those. But the exam is supposed to be a 75 minutes exam. Okay, but you have a 2 hours window. I think this should be sufficient. And because it's take home, so the exam is open to the textbook and to the lecture slides. Okay, and because it's open to lecture slides, it's also open to the lecture videos, but I'm not suggesting to look at lecture videos because I think that's going to take more time. Probably scan through the lecture slides will be an easier way to identify anything you find useful. But you're allowed to do that, to look at a video as well, but just think it's probably taking more time. Anyway, so yeah, this is basically the nature of the exam. And what I'm thinking is that, I will send you via email. I think this is probably more robust, a copy of the exam around 8 a.m., usually before, a few minutes before 8 a.m. I'm sorry, this exam should not be shared or discussed. I'm sorry, I'm missing a very important thing. Let me put it back. So, and then I'll email the exam to you. So you should be expecting that exam, okay? On March the 4th, I guess this is the day that we should not. Okay, the same day that we have on the calendar, and that overlaps with the lecture time, and you should receive the copy around, I think, 10 a.m. And you can work on the exam during the typical lecture time, right? But you have to work on this independently, although it's a take-home exam, but everyone should work on this independently. And you cannot discuss the exam with anyone besides me, or you cannot share the exam even after finish the exam. You can keep it as your personal copy, but do not share it anyway. Okay. Yeah, I may actually change individual copies a little bit, so that to make sure this is fair. But the difficulty will be exactly the same. I'll just play with some numbers. Okay, so that's the thing, the plan that I want to do this. And solutions of the exam should be returned to me via email as how you submit your homework by 12 p.m. Right? I'm going to give you the exams around 10 a.m. and you have 2 hours to prepare the exam, work on it for 75 minutes, and send it back to me no later than 12 p.m. And for this, because exam, so I will not accept any late submissions. So be sure that, or try your best to submit this as soon as you finish the exam. I will not suggest you wait for the last minute, okay? Yeah, the exam questions should be clear because I'll scan through these questions a couple of times before I post them. But if you have any questions for clarification, okay, you can reach to me and I will be available on Zoom to discuss. I think it's probably easiest. Yeah, I'll have a review lecture prepared before the exam, and I will review the fundamental concepts to be covered in exam and try to go through some example questions. Okay, but the questions will be similar to the ones you see in the homework. Okay, and for that, I'm done for this cluster. And again, thank you so much for for the time. I know that we have some accident, but thank you so much. I'll start recording now.